Good afternoon. Wow, I haven't stood at a microphone at this podium for a while, so I can do all kinds of goofy things. Anyway, hi, good afternoon. I'm Tony Dardis of philosophy, and it is my enormous great pleasure to host and introduce Dr. Eric Leonardis, who was a student of mine 12 years ago. And why don't I talk about him rather than us? So Eric is currently a postdoctoral fellow at the Talmo, Pereira, and Tom Albright lab at the Salk Institute for Biological Studies. He researches human and animal behavior using methods from systems and computational neuroscience. You can't hear anything. Is that true for all you guys in the back? Can you guys hear? I guess, okay, I don't want it to... Anyway, is it... It's going to get bad if I get too close. Okay, let's see. Using deep neural networks for behavioral tracking in humans and mice with an emphasis on deep reinforcement learning. They probably said that. Current postdoc project, behavioral study of museum viewer behavior at LACMA, the Los Angeles County Museum of Art. Eric's worked with Professor Andrea Chiba and Dr. Lala Quinn on neuroscience experiments involving social behavior towards other conspecifics and interaction with robots. He's worked with and helped manage interdisciplinary groups of students, research scientists, postdocs, engineers to acquire robotic, neural, and behavioral data, and then analyze that data using signal processing and dynamical systems methods. He was recently interviewed. He was recently wired and interviewed about body horror and insular cortex. We discussed an H.R. Geiger-inspired survival body horror video game, Scorn, and its relationship to embodied cognition and the neuroscience of disgust. And Eric shared with me that he's been asked by the National Academy of Sciences to vet a filmmaking project at NYU that is about horror, and he's supposed to check out whether they're getting the science right. So, welcome, Eric.
Thank you, Tony, for having me. And great introduction. That was fantastic. I wouldn't have it any other way. Thank you all for coming. So today I'm going to be talking about explaining AI, or really I'm going to be talking about why AI can't be explained. So I've tricked you all, but we're going to talk about some methods for trying to scratch at explaining these things. Okay, so let's get started. Okay, so as you may have noticed, especially this year, AI is increasingly affecting everyday life. As a professor, you may have noticed your students' essays have gotten quite good and yet fabricated a bunch of information about papers that don't exist. That's probably because they're using ChatGPT to do so. ChatGPT is one of these large language models, which is a very, very, very large artificial neural network. This is a type of model that takes artificial neurons that kind of vaguely mimic the brain in some ways and not others. And these algorithms are basically trained on the entire internet. You take the whole internet and you train these algorithms to try to predict each word for word. And then it turns out that they can learn a bunch of interesting relationships that can be useful or not useful, depending on how you look at it. So these models have been integrated into education, business and finance, law enforcement, and medicine, all of which have their own issues that we're going to start to disentangle in the latter part of the talk. Okay, so here's some warnings. The AI hype train is getting really, really big these days. There's all this talk about artificial general intelligence, that there's some kind of, we're really close to getting some kind of super intelligent AI that's going to take over the world and kill you and your family, and we're all going to die. That is the thing that you may very well hear from the folks in Silicon Valley. They want you to be, kind of scared, but also they're just going to keep developing them anyway for some reason, right? There's a bunch of contradictions here. So there's a philosopher, Nick Bostrom, at University of Oxford, who says that super intelligent AI is more of a threat to humanity than nuclear weapons. Yep. So there's another one, okay? So there's just a general question, should I trust ChatGPT with my life and my well-being? If it's super intelligent and smarter than all of the other humans, why not, right? What could go wrong? So anyways, I just want to sort of inoculate the crowd a little bit to this type of information because really I think this is a kind of bait and switch. What the strategy here, the marketing strategy is, well, we have the AIs, they're super intelligent, they're sort of autonomous beings, right? They're doing all this bad stuff, but that's not me, right? The corporation that has funded and put together this AI and unleashed it on the world to do all sorts of things, it's certainly not the corporation that is responsible for this. It is the super intelligent AI that is autonomously doing these things. So I just want to sort of generally point out that a lot of the problems with AI are actually just problems with late-stage capitalism. It turns out that that is really what's at issue here. And that's why we need to disentangle these issues. So just a fair warning, be careful of the snake oil. Be skeptical. We must be skeptical. Okay, so that's why I'm going to try, and luckily we're in New York, so this will actually make sense to you. What I want to do is I want to train the New York state of mind for AI. Okay, so I want to present a scenario where we have this guy. He's sipping on his Starbucks, and he stops you on the street. You're walking on Prince Street in Manhattan. He stops you on the street and he says, "Hey, listen, I'm not a doctor, but I did really well on the MCATs, and I think you have lupus." Okay? So what would you do in this situation, right? If you're in Manhattan and somebody says that to you, you would probably say an expletive, and then you would walk away, and you would not give it a second thought. Okay, wait, all right. Suppose maybe he had a point. Maybe you weren't feeling well, right? And you had a rash on your face that you were really worried about or something. What would you do then? Would you then take his word for it? No, you would not take his word for it. You would probably go on WebMD and convince yourself that you have actually this disease, and then go to a doctor and try to figure out if you do or do not have this disease, right? So this is we must be skeptical. We cannot take these things for granted. Okay, and we should not just blindly follow whatever some intelligent AI tells us, right? Double check and make sure that it makes sense. Okay, so now I'm going to talk about algorithmic transparency. So we have all of these AI algorithms, right? And a very a classic way of looking at this is whether the code is open source versus closed source. Okay, so if it's open source, that means it is publicly released. All of the code is available for us to look at and try to understand. And then if it's closed source, that means a proprietary, opaque, basically the company has taken this and made it so you don't know what's inside of the software, okay? So delightfully, OpenAI was an open source AI software. It got really popular with ChatGPT, and then they made it closed source. So they made all of their code not available anymore for people. And yet they're still called OpenAI, which is almost ironic in a sense. So the issue at hand is that we must be able to be transparent. We must be able to explain how these AIs are working when things go wrong, okay? And also, one issue is that open source doesn't necessarily mean that it's transparent. That is to say, I could send you 300,000 lines of code and say, good luck understanding this, right? Without any comments, without any documentation, without any support. And in a sense, yes, it's available, but also still not very transparent for us to understand. So we also need to be transparent about the impacts that these have, the actual material consequences of these algorithms in everyday life. Okay, so taking a step back, because I was a history major, I have to do this every time, and I torture my students with it. We're going to go back to World War II. All right, so Norbert Wiener, the father of cybernetics, was sort of gained popularity for automating a 13-man process, which was an anti-aircraft process. So you have 13 different people. One of them is recognizing that there is a plane. The other person, then they're calling on the radio to another person who is then calculating what are the coordinates of the current coordinates of the plane, then saying in the radio what those coordinates are. Then you have somebody else who's trying to predict where they're going to go. Then they're going to calculate those coordinates and so on until somebody cranks the gun, and then the missile is fired. So what Norbert Wiener was able to do is he was able to turn this into essentially a zero-person process, right? You make an automated system that does each of those 13 different information processing steps, and that allows you to have an automated machine doing this process, okay? So I just want to put this in the context of AI is just another type of automation. It happens to be a very powerful type of automation, but it's very much doing the same types of things. You're taking some process that people are doing, and then you're trying to automate it in a machine. Okay? And this has a very long history. This is not something that's suddenly new and fundamentally different. Okay? It is another type of automation. Okay? And classically, even back then, even in the aircraft case, the anti-aircraft gun, they use something called error, which is essentially what is the error? Where is the gun currently pointing? And where is it supposed to be pointing? And then how much do I have to turn this crank to point it in that direction? Okay, another example is a thermostat. Okay, so your thermostat, you set it to 71 degrees, and it's 72. So the error is 1 degree. And then what you need to do is, you need to cool down the room to get it to your desired goal state. Okay, and neural networks also have error functions. Right? Error functions are the ways that we are going to be able to train algorithms and evaluate whether they're doing well or not. Okay. Then there's the first artificial neural network by McCulloch and Pitts in 1943. They introduce a network of units which can perform logical operations. Okay. And depending on how many of these units you have, you can do more complex manipulations of data. Okay. So here's the only equation I'm going to show you today, and I hope it looks familiar. Who's seen this equation before? Raise your hand. It's not there. Oh, there it is. I don't know how that works, but okay. This one. Who's seen this equation before? I know you've all seen this equation before. Okay. Y equals f of x. Okay, so this is a function that transforms an input x into an outcome y. All right, so neural networks are also known as universal function approximators, which means that any function that you could imagine, any input-output relationship, could be transformed by a neural network. Okay. A lot of times we feed in images as inputs, and then we spit out, is this a cat or is it a dog as an output or something like this. The neural network is the function that is transforming the input to the output. Okay. The problem is that neural networks are not that easy to explain. In fact, often they're referred to as black boxes. Okay. That is to say, the input is put in, something happens in the middle, and then the output happens. We evaluate that using this error metric, and hey, it works. And, why do we need to know about any of the details about what's happening inside, right? Okay, so there's a picture. Just to really, really ingrain it here, you have the input, x, you have a function that manipulates it, and then you have an output. It looks very complicated and scary, but when it comes down to it, it is y equals f of x. Okay, cool. Neural networks are actually able to do really interesting types of classifications. So suppose that you wanted to separate two types of data. Traditionally, we would use a line, just simply a line to separate these two groups of data. A very simple neural network of only a few units could do something like this. And as you want to do a more complicated transformation, like for instance this circle, you would have to add more units to your algorithm. Okay, so they do non-linear transformations of data rather than linear transformations. Okay, neural networks use training sets and test sets. Okay, what you do is you have things like labels or things like categories that you want it to be able to train on. You feed it into the network, you calculate your error, you manipulate your network to fit to your training data, and you hope that it generalizes to your test set. Okay, that is how these things and machine learning in general works. Okay, here's a diagram where we have error on the z-axis, and then we have different weight parameters, which are these parameters inside your network that it's manipulating to make the error go down. Okay, the goal is for when you're training this network on your training data, you mess with the inside of the network and the connections between these units, and you try to make error go down. When error go down, good. Okay, excellent. So we call that gradient descent. It's a hill climbing or hill descending algorithm to try to make error go down. Okay, cool. So here's like the type of decision boundary that you might want, right? Let's say I have this spiraling pattern and I want it to separate each arm of this spiral. Okay, neural networks are really good at doing this type of thing. They can figure out any arbitrary nonlinear pattern and you can train it to do so. Okay, you can also use things like this. You would feed in an image and it would spit out, this is a dog, this is a bird, this is a cat. This is considered classification. Okay, all right, so now I'm going to give some examples of neural networks that we work with. And then after that, I'm going to talk about how we can try to explain what's happening inside this black box. And then we're going to talk about ethics after that. Okay, so I'm a neuroscientist, so I'm interested in how we can leverage these types of systems to understand the brain and behavior and the body. Traditionally, we think of in robotics as there being sensors, something that happens in the middle, which is the controller, and then we have effectors, which are actions in the world. Okay, then the robot or system acts. The physical world then gives it new sensory information, and you have a feedback loop, which is generated. Now, what we're interested in our lab is how about the brain and the spinal cord and muscles and the body? What role do they play in these types of transformations? Okay, so here is some of the predictions from the neural network in Talmo lab that we're working with at the Salk. This is done with a program called SLEEP. That's Social Leap Estimates Animal Pose. And what we're trying to do are feed in videos of different animals and predict where their body parts are in an image so that we can understand movement and behavior. Okay, so we have done this with many, many different species, as you can see on these diagrams, in an effort to quantify different behaviors and figure out the relationship between the brain and behavior. Okay, so what kinds of applications can this be used for? So I'm going to talk about some useful applications, and then we'll talk about some harmful applications later on. So what we're using it for right now is to quantify animal behavior, as I just said. We're using it on disease models like ALS, Alzheimer's, cancer, and aging, trying to figure out how behavioral changes may underlie these diseases and how we can potentially diagnose these diseases early based on the types of behaviors that we may observe. Okay, we're also working with NASA on no-gravity spaceflight. We have a bunch of mice in space, and we're trying to figure out, well, there's a bunch of people who want to go to Mars. I don't want to go to Mars. I think it's a ridiculous thing to do, but people really want to go to Mars, and that's fine if that's what you're into. And the idea is if you want to go to Mars, it'll take about 3 to 5 years to fly there, and you'll have no gravity. Okay, and it turns out we don't really know what happens to the human body in long term when you're not in gravity. So what happens to your tendons? Do your tendons atrophy and then your muscles don't work? And then when you get to Mars, you're not going to be able to move around. This seems like a big problem. So that's why we're trying to figure out how these behavioral changes and movement changes happen with these mice in space. But in general, I'm more interested in how the brain controls the body. We're also working with things like plant biologists to track how roots can grow through dirt in an effort to make deeper roots that can basically take carbon from the atmosphere and keep it in the the dirt in an effort to fight climate change. So there are some useful things that these neural networks can do that are probably worth trying. Okay, so here's our example. This is a raw image from a video. Okay, it's not. There it is. All right, I don't know why. That is so bizarre. But it's there. Okay, cool. All right, so we feed in these raw images. We feed it into a neural network, and then it spits out a probability that this is the tennis player's right wrist. Okay, so that's the transformation. That's the function that those networks are using, right? You take in a raw image as an input, you do something to it, it spits out where is the wrist. Okay, and you do that for each individual body part. Okay, so here you can see it. Those probabilities that it's spitting out are called confidence maps, and you do that for each individual body part. You can't see that, can you? Okay, no, there it is. Okay. So you do that for each individual body part. Then you take the maximum point of that cloud of probability, and then you get the position of each of those body parts out. So you can see all of the legs, the wings, the eyes, etc. for this fly. So my advisor works with flies. That happens to be one of the examples. Okay, so here, this is an example of training. So we have error. We already talked about error on the y-axis. And then the x-axis is sort of how long it's been trained for. How many batches of labels have you fed it? This is also an important point that in these types of data, I need to label them first. To create a training set, then you feed it into this network, it learns to minimize the error, and then it will generalize to the rest of the data. Okay, so maybe I feed in 100 labels, and then it fills in the 100,000 frames that I wanted to fill. Okay, so when it's started, so when you see it says epoch 1, that's at the beginning. So you see those error distances in that little diagram are really, really big. As you train it, they become smaller. Okay, so that means the predictions and the labels match better. Okay, that is how we are training these networks, and that is what training would look like. Okay, what we want to get out is we want to get out quantified data of those positions of those different legs. So we would spit out this time series of positions over time to try to get a sense of behavioral dynamics. So this is what it would look like if a fly was walking, and this is what it would look like if a fly was grooming its eyes and its antenna. Okay, so you can see there's actually a clear difference in those dynamics. This one looks a little bit arrhythmic, but there's still some kind of pattern in there. And this one's highly rhythmic, the gait pattern, right? Okay, cool. So that's just an example of the type of stuff we're doing. What's interesting is that it's not quite a black box. That is to say, if we take some of these, there are these things called hidden layers that are happening inside this network. Okay, and each hidden layer basically is in charge of extracting certain types of information. So if I have this image of this face, the first hidden layer is going to extract edges. Okay, the next hidden layer is going to extract combinations of edges. You can start to see eyebrows and eyes and noses and things of that nature. And then the last hidden layer is going to actually extract faces, whole faces, right? And use that information to try to classify either where those things are or what those things are. Okay, so we can actually visualize what's happening inside of these networks. It just so happens that sometimes it's easier than not. Okay, so in this case, we do have some kind of idea what's going on, these sets of transformations that are happening from layer to layer. Okay, an interesting thing about these networks is the work of Dan Yamens and DiCarlo, which is basically that if you train one of those networks, okay, cool. Then you can actually predict real brain activity in the visual cortex, usually to about like 40 to 60% accuracy. So we know that there's also a hierarchy in the brain for these visual areas which extract edges, combinations of edges, and faces, and things of that nature. So they can actually roughly do similar types of process to the brain, but they're not really great models of the brain. The types of neurons that are in artificial networks are not nearly complicated enough to be able to capture what real brains are actually doing. But they do capture something. So we can probably learn something about the connections between brains in an interesting way by looking at these types of models. or brain cells, rather. Okay, some work going on in our lab by Adi Prasad found that it really depends on what type of data you train it on. So if you train this network on clip art from Microsoft Word, then it's not going to generalize to brains really, really well. But if you train them on natural images that you may actually encounter in the world, then they predict brain activity much better. Okay, cool. All right, so now we're going to talk about the body. All right, wait a minute. Is this? Oh, we already went through that slide. Okay, cool. So this is some work being done with our collaborators, Josh Merrill, Diego Alderando, and Benza Olvexi at Harvard. What we're trying to do here is actually create virtual simulations of bodies, okay? And these are rodent bodies in this case, of rats. So we have a skeleton, okay? And then we have some actuators and motors inside of the skeleton so that the rat can move around the environment. We train it to do things like jump over different gaps, to collect these different blue balls in a maze, to escape a bowl, and this hilly type of region, and also they have to touch this yellow sphere 2 times within 1 second. Okay, so the idea here is that they can actually learn different skills. The same network can learn different skills and then generalize across these different scenarios. Okay, so to do so, we use something called reinforcement learning, which is also a very popular method. So basically what's happening is we have a neural network that is making some kind of action. It then runs through the environment. The environment produces a state or an observation, like where are you now that you've just moved, and it gives you some reward based on that operation. Okay, so there's this feedback loop of acting and sensing, and then getting a reward. Okay, so also there are 2 different types of network inside of our rodent. One of them is called the actor network, which acts and moves around. There's nothing there. Great. There we go. Okay, cool. So there's an actor network and there's a critic network. So the actor network decides what movements you make. The critic network says that was a good movement or a bad movement, depending on whether it will give you reward or not. Okay, so it's trying to estimate the expected future reward. Okay, so these 2 networks kind of work together to try to figure out what actions you should be taking to complete a task. Okay, cool. So here's a video from Merrill et al. 2019. This is to give you an idea of what these types of artificially controlled bodies look like. On the right, this is basically a visualization technique to try to see what types of dynamics are occurring inside of the virtual brain. Okay, so what they've done is they've taken, these thousands of neurons. I think it's a 3-layer network with 256 neurons in each one, and they try to lower the dimensionality and see if there's any dynamics that are generating this walking movement. Okay, so let's take a look. Okay, so you can see there in the policy that there is this rotational dynamics that's happening in the neural network activations. Okay, and that every time the rat is running, you see that type of rotation in the activations. So you actually have a sort of dynamic generator that's generating the behavior in the brain activations themselves. So this is another case where we're kind of scratching at this black box, getting a sense of what's happening inside of these networks when these virtual animals are behaving. Another thing is that these physics simulations that we have here, it does look kind of silly, but these are some of the most advanced physics simulations that we have. They're simulating friction and tension and all sorts of different things that you would use for biomechanics. Okay, cool. All right, so there's this other thing called representational similarity analysis. Now, what that's doing is basically saying, take all of the things that are happening in the environment. Okay, so you take all the different behaviors that are occurring, you take all the different forces that are at play, joint angles, posture, etc., and then you try to see which artificial neurons are correlated with these different things. So we can basically say that there are some neurons that represent joint angles, some that represent posture, some that represent different behaviors and forces and things of that nature. And this is another effort to try to figure out what is happening inside of this black box, right? It's pretty crude measure. It's just kind of basically asking what's correlated. It is, in fact, not a causal measure, so it's not necessarily going to give us what we really want, that nice causal explanation. But this is a method that can at least start to tell us what's happening inside this black box. Okay, cool. So back to this black box problem. What's going on with that? Okay, so there's this new field that's coming out of the machine learning literature. Some of the work is by Neil Nanda at DeepMind, which is called mechanistic interpretation and explainable AI. All right? So this is an attempt to interpret the neural network in a mechanistic manner, to try to figure out how these small units are collaborating together to create these different behaviors. It's a type of reverse engineering, trying to figure out, after you've trained them, what is it about the organization of the units that is giving rise to these different behaviors and functions. Okay? So can we look into the network and say, there are these motifs, which are these relationships. Let's say there are these 5 neurons, they're connected in this very specific way, right? You find those motifs, and then we need to figure out like what functions they perform. Maybe they're transforming the edges to the combinations of edges, or maybe they're deciding which action to take, whatever that may be. That type of information. So what are the motifs that emerge, and what do those motifs do? We actually have methods for trying to figure this out now. So there are other questions like what changes during learning led to the higher network performance? And can we quantify those changes to try to figure out what's happening in these black boxes? So these are not full explanations yet. They are merely interpretations in an effort to try to explain. Okay, so I would say they're not successful explanations of the behavior, but they're certainly starting to make this black box a little bit more interpretable. Okay, cool. So at UCSD, I took quite a few classes with a philosopher named Bill Bechtel. He is known for the new mechanism movement and the new mechanistic philosophy, which is a type of philosophy of science which is concerned with when is an explanation successful, okay? And when have we produced a mechanistic explanation, which is going to tell us quite a few things. So in this perspective, what we want to do is we want to characterize the phenomenon to be explained, okay? We want to identify what components are part of this phenomena. We want to figure out the causal relations between the components, and then we want to figure out how those components are organized to produce the phenomena. Okay, so here we have a mousetrap. Okay, the mousetrap has these different components that are organized in a very particular causal way. You have your trigger, your latch bar, and your catch. When you push down the trigger, the catch opens, the latch bar is released, and then the impact bar comes down and hits your mouse. Okay, this would be a type of mechanism. This happens to be a very simple mechanism. We are not limited to simple machines. There are lots of mechanisms in biology that you may be familiar with, like ATP, mitochondria, all of our little cellular modules in there. Those are all mechanisms that perform certain functions. Okay, so this may be a simple example, but what we really want is we want a mechanistic explanation of neural networks, and we do not currently have one. Okay. It turns out that they're very hard to be able to produce such an explanation that really will be able to predict its behavior. Okay, so what would a mechanistic explanation look like? This is one of the diagrams from Carl Craver's book, which is basically, and I remember seeing this in Tony Dardis's class and being like, yeah, this is the thing. And I got very excited about it, but it's not really, I mean, it's not too exciting. Basically, so you have multiple levels of organization in a mechanism, right? So we have a function that's being performed, which is this higher level part of the mechanism at the top, but we want to know how the parts inside work together to produce it. This is the type of explanation that we don't have at this time with neural networks. And this is the explanation that I think we should have. And in fact, I would argue it is an ethical imperative that we have them, especially if these neural networks are being ingrained in our everyday lives. If we're using this for medicine, for law enforcement, and etc., we need to understand how these algorithms work in a mechanistic sense. Okay, so what would a mechanistic explanation look like? You would have these different motifs of connections between these neurons. And then we would have to figure out how those motifs allow for the transformation of information in this network. So we used the past example with the edges and combinations of edges in this image processing task. We want to figure out how these motifs perform functions to perform the task. Okay? And we can basically create quantifications of these motifs and try to intervene on them and figure out what they actually do. Okay? Cool. So here's a really early attempt at causal intervention. So this idea would be very similar to how a neuroscientist might approach the problem. The idea is that you would either silence these units from activating, or you would stimulate these units and make them active, and then try to observe how that changes behavior. Okay. So here we would look at the first behavior is rearing. That's like when the rat or the mouse goes like this on their hind legs. We can actually inactivate neurons to stop this rearing behavior from happening. So depending on which neurons those are, that may be one of the neurons that produces said behavior. Okay. Same thing for spinning and jumping. If we inactivate these neurons, we can reduce the amount of spinning and jumping that occurs. Okay. And the last one, this is, I think, oh no, that's not spinning and jumping. The second one's jumping. I don't know why spinning is that? Yeah. Spinning's supposed to be on the bottom. Okay. So spinning, the last one, this would be if you stimulated certain neurons inside of this artificial network, you can actually make the rodent spin around. Okay? So depending on what units they are, they have certain mechanistic relationships to the behaviors that they're producing. And we can actually intervene at the lower levels to try to make the higher levels change. Okay? This would be like a scientific process that we need to do for virtual networks as much as we do with biological networks. Okay? So this is like a very early attempt at trying to causally intervene on these networks, but I am pretty hopeful that we'll be able to do this in a systematic fashion and try to produce a mechanistic explanation for how these networks actually work. Okay, ethics time. You guys ready for ethics? Great. So, as I said, mechanistic explanation is critical for ethical AI because we want to know what is happening in these systems that are being used. I heard different examples like, they're going to put a neural network in charge of college admissions. Wouldn't you like to know how that works? If it's choosing who gets into your college and who doesn't, right? These networks are going to trade your stocks for you. These networks are going to diagnose which diseases you have, and yet we don't know how they work. This seems like a bad thing to do. We need to not move fast and break things, right? That's what the Silicon Valley people say. Move fast and break things, and we'll figure it out later. The problem is the incentive structure is all wrong in late-stage capitalism. The incentive structure says, yeah, just do it. Who cares what happens, And then what's going to happen is we're going to have some major scandals and some major atrocities committed by these networks because we haven't taken the time to make sure that they're safe. Right? And how can we make sure they're safe? We have to figure out how they work. Okay? So another few things that are sort of ethical issues in machine learning are especially these large language models like ChatGPT that are so popular, these chatbots. Training one ChatGPT, okay, uses the same electricity as 1,000 US households for 1 year. Okay? It takes about 6 months to train one of these. And basically, I'm thinking what we should measure this in is like, how much of the rainforest are you burning in order to get your network trained, right? It's also probably not necessary, this is my opinion, it's probably not necessary to train something that's so large, right? Some of these large language models have 175 billion artificial neurons, okay? I don't know how we're going to try to explain what's happening there when we're using such large networks. Most of the ones we use are much, much smaller. So when you take the entire internet and you train it on 175 billion units, okay, this is going to leave a big carbon footprint, and it's going to be really, really hard to interpret. It just so happens to work, but I don't think there's any reason why we can't have a much smaller network that does the same thing. We just need to figure out how they work. Okay, and also another issue is that the training set for these machine learning algorithms are often used regardless of their copyright relations. We know a lot of artists are having their work replicated, and they're not getting any credit for it, and they're not being compensated for it in any way. Okay, so this is a significant issue. So another issue is bias and racism in computer vision. Okay, so this is based on some of the work by Abiba Burhain and colleagues, which is basically that the training sets that we're feeding in, the entire internet, which includes 4chan and Reddit and Twitter and Facebook and everything, right? These training sets are unequal. That is to say, they're a very particular perspective, especially like Reddit is a very white male perspective, and they're biased against minorities. So curating these data sets is critical for training these algorithms. Okay, so we don't want to perpetuate the biases that we have in society, but when you train a network on the whole internet, that is exactly what you're doing. So she sort of painstakingly went through some of these data sets that they're using to train these networks and found misogynistic materials, pornography inside these networks when they're being trained, stereotypes, all sorts of really, really undesirable data that they're training it on just because they haven't taken the time to look. They haven't just gone through the data set to see what they're training it on because, well, that's labor and, that's going to cost money. So that being said, there are some warehouses that they've sort of outsourced labor to places like the Philippines, places like India, where you have like 1,000 people at a computer and you just flash all of these horrific images, right, of, pornography and murder and assault and so on and so forth. And you say, is this bad? Should we include this in the data set? Yes or no? And their whole job is just being flashed with this horrible, horrible images. So there's also been some work done on content moderators showing that it's a highly stressful job. There's a lot of mental illness that is essentially caused by doing this type of job. Right, so their answer is, well, we're just going to try to automate it, but then, then you have the same issue, right? So what you feed your network is critical, right? And if we take the time to curate those training sets, then that would be one way of alleviating a lot of these issues. Okay, so to quote Burhain and Prabhu, feeding AI systems the world's beauty, ugliness, and cruelty, but expecting it to reflect only the beauty is a fantasy. Yeah, you're feeding in all of this garbage, and you're expecting it to come out and do Shakespeare or something like that. Okay, so some other issues that I think are very, very worrying are predictive policing. Okay, so in predictive policing, there are a few different types of predictive policing algorithms. So one of them are recidivism models. So this would be usually if you're in prison and you've been in prison for 5 years, something like that, there are these companies that will try to evaluate how long you should be in prison for. How do they evaluate it? They use an algorithm that they won't tell us how it works. It's a proprietary closed source algorithm, and they decide, okay, based on this person's name, their hometown, their ethnicity, how long they've been in prison for, the nature of their crime, et cetera, they should be in prison for another 10 years. And then that is then given to the judge as evidence for whether or not they should be given, put on parole, et cetera. So this is a big issue. We need to be completely transparent about these things. We cannot have proprietary organizations deciding based on some algorithm, which we don't even know if it's a neural network. We have no idea what it is, actually, to decide who stays in prison. Okay? So there are courts in 24 states that use this right now, to give you an idea of what's going on. So another thing is predictive policing in terms of enforcement. So police are going to be sent to specific areas to patrol. So there's algorithms for deciding which areas do you patrol. So it turns out police collect a lot more data and have collected a lot more data from communities, African-American communities, Hispanic communities. So the algorithm, of course, says, well, you must patrol those areas, right? So this is another way that biases are being perpetuated in law enforcement. So that means, like, you haven't even committed a crime. The police are only looking in one place, and that's because an algorithm told them to do so. This is very dystopian stuff, right? And not only that, once again, we don't know how the algorithms work, and they're not going to tell us how they work. Okay? So these things are perpetuating these biases. I also have an example from San Diego, where I live. So what happened was the police installed these streetlight cameras and microphones into the streetlights, so that way they could watch everything that we do and catch crimes. Yes. So they're surveilling us through our streetlights, and basically the community of San Diego came together, and we went to our city council meetings, which I had the pleasure of attending, and we said, no, we will not stand for this. This is absolutely ridiculous. And as a result, interestingly enough, by the work of people like Lily Ronnie and other influential members of UCSD at San Diego, we're able to get them to decommission the streetlights in San Diego so that they do not use them for surveillance. So we've basically got them to turn off the cameras. The police, as a result, lost millions and millions of dollars. They were not very happy about that. And that was about 3 to 5 years ago. So what happens this year? The mayor decides, hey, those streetlights were pretty cool. Let's spend another $200 million to put some more in there because the other one's broke. So here we are again at the city council meeting trying to stop these algorithms from being used for predictive policing and perpetuating these biases. So we don't really know whether they're going to be putting them back. We were successful once, but you really have to be persistent with this type of activism to make sure that it stays that way, because the second that you sort of put down the ball and go back to what you were doing, they'll just put them right back. Okay, so there are some people that are trying to actually use data science in order to alleviate some of these problems, like Paula Villarreal, the ACLU Data for Justice system, which is basically advocating for the victims of algorithmic oppression, basically trying to quantify racial bias in policing and then trying to use that data to make arguments against it. Right? So we need to advocate for change at the level of policy and law for correcting these injustices. And those injustices include not only data bias, but also privacy concerns. So the privacy concerns, like the street cameras, would be like a privacy concern. For medical algorithms, there are a bunch of privacy concerns, which are going to, release your personal data by accident. ChatGPT has this one glitch, which is really fun, which basically what it does is it accidentally gives people your username and password. Yeah. Whoops. Whoops. This is Eric's password. Anyway, what was the question? It does weird things like that. They're called data leaks. And that's another reason not to give it your password, by the way. Do not type your username and password into these things because they will remember them and regurgitate them just about at any time. Usually this only happens, 1% of the time or something like that. 99% of the time they're doing really useful and useful things, but every once in a while they will do a complete violation of security and privacy. So that is another thing to be careful of. Lack of transparency is another one. We can also try to quantify lack of transparency in those 24 different courtrooms and try to make those algorithms at least more transparent so we can know what's going on, and so on. All right, misinformation. This is another thing that is really quite tricky. So who's heard of deep fakes? Some people have heard of deepfake. That's good. That's good. All right. So deepfakes are these generative images. A neural network will generate an image that is completely fake and never happened. Right. In some sense, when they were just starting, they were kind of easy to tell what was fake because you'd see like their right hand had 5 fingers and their left hand had 7 fingers, and you go, okay, so that's probably a fake image. People don't generally have 7 fingers. But as they get better, it will be harder and harder to tell. Like this guy transforming his face into Tom Cruise. So my thoughts about deepfakes are thus. So back to the New York state of mind, okay? Somebody calls your house and says, I am a prince in another country, and I need you to send me $10,000 right away so that, you don't get, so something bad doesn't happen. Sure. Okay. No, thank you. Goodbye. Close, hang up your phone, right? Another case is like Photoshop, right? I mean, we've had Photoshop for years. People have been doctoring images for a in fact, since the camera came to be, people have been doctoring images since the 19th century, right? So this is not necessarily fundamentally new. It's just that we would need to approach things like deepfakes and images in the same way we would try to tell if someone Photoshopped it or someone was giving you a crank phone call. There was a recent case where Joe Biden was calling people's houses and like saying horrible things to them, right? And it sounds just like Joe Biden, but I'm not going to say it because I'm being recorded. Anyway, but you can imagine all the expletives he's saying to you, and he's telling you, he's talking about your mother, et cetera, and you're like, I'm not voting for that guy, But that is just going to be another thing, right? Audio deepfakes, right, that we're dealing with. The difference really is in scale. It's actually photoshopping things takes time, right? So your best Photoshopper is going to take quite a few hours to doctor this photo. Deepfakes are going to happen much more rapidly. So it's really a matter of scale, right? Misinformation we've always had, but how much misinformation are we going to have? That is the real issue at hand here. So my best advice is to be skeptical. Train yourself to not take everything for granted. We talk about post-truth society and things like this. I don't think it has to be like that. It just means we need to be double-checking the things. Don't believe everything you see, right? Don't be gullible. But sometimes it's really hard to tell. And sometimes we just don't take the time to check. Like I look on the Twitter thing and I see, this video of somebody saying something, I just assume, it's probably real. And especially if it matches with my belief system, then I'm much less likely to double check, right? And for this election, this is going to be fun. This is going to be a great election year. We're going to have lots and lots of deep fakes and lots of AI misinformation. So be ready. Be ready, folks. All right. So this was a paper that I found very interesting. This was by Lucy Suchman. She's an anthropologist and cognitive scientist. And she wrote this paper called The Uncontroversial Thingness of AI, which is basically that, this AI is its own thing. And it's not related to the person that set it out into the world. It's just its own thing. So this is the mechanism for diffusion of responsibility. It wasn't me that did it. It wasn't the corporation that did it, that, paid for it to be done and then released it into the world. It was the AI, Don't blame me for that, right? And this diffusion of responsibility also, one of the analysis that Lucy Suchman did was in drone strikes. So you have, your AI deciding which target to select, whether that is the target or not, and whether to fire. Right? So there's this question of who's responsible for that, right? Let's say it makes a mistake and it shoots the wrong person, right? Well, whose fault is that? It's not my fault, the one that literally, charged the drone and then, sent it out into the world or poured, I don't know if they use gas. I have no idea. But it's not their fault for sending the drone out. It's the drone's fault. It turns out that this is a very common way of thinking in this literature, in machine learning, right? So I think we need to sort of combat this idea. It is not its own self-autonomous system. It is very much something that humans are actively pursuing and doing, okay? And the more that we ingrain ourselves with that type of mentality, the more chance we have to protect ourselves. Okay, so here are some general lessons of AI literacy that I was hoping to impart with you today. When we find out about an algorithm that's being used in society, we should ask, is it open source? Is it explainable? Is it interpretable? If not, that's a problem. Who are the humans involved in setting it up and deploying it? Who did it? What is their funding source? Who is labeling the data set, right? Because that's also very unclear a lot of the time. And where did the data come from? If you ask these questions, you will be guaranteed to frustrate a lot of machine learning folks. Also, so actually earlier in John Tian's class, somebody asked about the EU. which is very interesting because the EU has a much better record of regulating things like social media and the internet. So I actually found that basically this month they have passed a AI Act of 2024, and it's very interesting. It basically is an attempt to put safeguards on general purpose artificial intelligence. It limits the use of biometric identification systems by law enforcement, just like we were talking about in San Diego. It bans social scoring and AI to manipulate and exploit user vulnerabilities. Okay, so trying to get you to give up your password and all these other things for security purposes. And it also gives consumers a right to launch complaints and receive meaningful explanations. There's the explanation word again. So the EU is very concerned about these unacceptable risks. They have a whole risk management system in terms of AI. And what they would consider to be an unacceptable risk would be this type of social scoring, using facial recognition to in public places, and these things called dark pattern AIs, which are basically like when you log into a website and it's like, take this fun quiz, tell us the 10 things about yourself that you'd like to share with somebody, and then it's like, where do you live, how, what's your ethnicity, blah blah blah, and people are like, oh great, I love quizzes, and then it tells you like, oh yeah, you're Jennifer Aniston, which member of Friends are you, that type of thing. But really what they're doing is they're just harvesting your data, right? So this has basically really upset the EU, and they have started to put some safeguards in place to make sure that they can't do that. Then some things that would be considered high risk would be like using these systems for education, employment, justice, immigration, law enforcement, things of that nature. Talk about immigration. ICE was using these algorithms to decide which people to keep in detention and things of that nature. Pretty disturbing. Limited risk would be these chatbots and deepfakes and emotion recognition systems. I don't know why that's a limited risk. It seems kind of like a high risk still, but whatever, that's fine. And then minimal risk would be like video games and spam filters and things of that nature. Okay, so the EU is actually making efforts to try to regulate these things. And we should certainly use this as a model in the United States. The United States is the Wild West. You can basically do whatever you want with these things, and it doesn't matter. There's no rules. There's no rules whatsoever because of free enterprise. Yay! Good old American ingenuity, making sure that we perpetuate the biases in society forevermore. All right, thanks. It was kind of a bummer to end on that. I apologize, but do we have any questions? Questions? Yeah, we got to go on the mic because it's videotaped. Yeah. So if you have any questions, come up to the microphone and tell us what you're curious about.
Thank you so much for, this was amazing. I have many questions, but I'm going to try with just one of them. How many of the concerns you have about AI is new, is unique? For example, I don't know, I can see so many parallels with the development of nuclear weapons, for example. So many things are strikingly similar. And I can see that so many of the issues you raised up, for example, about the impact on the environment is not unique. It can happen with Bitcoin data mining, right?
Bitcoin, don't even get me started.
Exactly. So what is unique? What is a unique concern that is just for AI that is not applicable to anything else in your mind?
Yeah, that's a really good question. What's unique about it? I would say the one thing that I could say that is unique about it is the scale of this decision making. Previously these biases exist, just like you're saying, and they were enshrined in other machines, right, and things of that nature. But we're talking about sort of automating at a much larger scale, so that we can, these sort of errors or mistakes will be propagated to way more people, right? So I think that's the one major concern. Because I do think that it's an important point that these things have already been around. There's not much that's new. And that was kind of the point about the automation thing. Automation's been around, right? And it has, transformed labor and society for a very long time. This is just the next iteration. But I do think in terms of scale and, the rapidity of response of these systems, that's what's going to be the biggest difference, in my opinion. Do you want to, is there, okay.
It's much easier if you do this.
Okay, sorry. I thought you were going to ask a question.
Okay, so I just wondered if you would like to talk a little bit more about curation, or the problem. What I'm thinking of is the problem of curation. I may be excessively paranoid about this, but if you train, say, ChatGPT on the whole internet, you can't curate the whole thing. There's just too much stuff there. You can filter out some of the obvious stuff. You can make people suffer by having them filter out the stuff that is remaining there. But you're also, what you're doing is training it on the data that's generated by the societies that we live in, primarily the English. I mean, we're talking about the English-speaking ones, and so we're talking about the United States, England, all the English-speaking parts of the world. And these are, I mean, look, this is arguable, but this is the way I'm seeing the world. It's a world that has got bias deep in its genes and bones. And so curating isn't going to solve the problem. That stuff is going to stay in the systems, and it's going to keep reemerging. And I was just sort of noticing, last fall we read a neat article about spam filters. Spam filters are good for trimming out certain kinds of. Anyway, actually, you know what? I'll leave that for later. So,
okay.
What do you think about curation?
Curation? No, I mean, this is a big problem, right? I think the answer is just don't train on the whole internet. That's my answer. But there's a few things that need to change here for this to actually work. If we want to do the same types of things with these networks that are trained on the whole internet, what we need to have are networks that don't require that much data to work, which means we need to figure out how these things work and make a network that's not 175 billion parameters and make it much more manageable. And then that way we can train on much smaller curated data sets if we actually have systems that don't require the whole internet to work. I think the scale thing is really the innovation that they had. Oh, we can just have so many units and train it on the whole internet and we get this result that's rather nice. But I don't think that's required. I think it just so happens to be what worked, and they didn't have to do much extra to make it work. So I don't think we should, take the whole internet and then, curate it. I think, like you said, that would be like torture. Although if we do keep using these models, something like that might be required. I don't know if we have to do it as a society or something like that, but that would be kind of nightmarish, So I think the curation issue is really challenging. But I do think if we have better networks, we won't need that much data. So smaller networks that are organized in a more effective fashion, that would require less data that we can actually manage. That would be my answer. But also that doesn't exist. So we need to get there somehow is basically my answer.
So this is a bit of a convoluted question. You were talking about AI with certain things like, I forgot what you called the voice one, but there were like deep fakes and then like the voice one as well. And this kind of goes along with what you just said, that if AI gets to a point where it's kind of more, I guess, singular, like this is AI and then like it has all of these other applications, do you think then it could be used to like spot things like that? Because like to the human eye, the picture that you showed, I was like, oh yeah, like that's Tom Cruise, and it wasn't Tom Cruise. But like it was his face. So like for us to like not be able to spot that, is there a way, since like we have to train AI to recognize the things that we recognize, since AI is kind of performing those tasks to make it unrecognizable to us, does it then also make it unrecognizable to the system itself, if that makes sense?
Yeah, that definitely makes sense. And there are already systems that kind of do that. And I think that is definitely one way to go that can help. So like the classic example are those plagiarism detectors for like professors. They run it through Turnitin.com. That's not a neural network, but you know, it's that type of thing where you say, is this plagiarized from somewhere else? We have networks now that can say, was this generated by a large language model? What is the probability that this was generated by an AI? And it turns out they're actually really good at figuring that out because there's basically something about, we were saying that these networks spit out probabilities, right? And that's what they deal with. So if you find like a page that was generated, like a bunch of text that was generated, and they all have like these same probabilistic structure that this network would use. It's like high probability words, low probability words. If you have like a high percentage of high probability words, then likely this is a network that generated it, not a human being. And they're actually like quite good at being able to tell whether it was generated by the AI. You can do the same thing with deepfakes. So we can actually use it to try to vet itself and make sure what's real and what's fake. But I'm sure that there are still some errors. It's not going to be right 100% of the time, but it could certainly filter out a majority of these things to make sure what's a deep fake and what's generated by an LLM. I think that's definitely a good way to go to try to protect ourselves from misinformation.
Come back.
Hi, I wanted to maybe pick up on Tony's question about the curating, because I'm thinking that by itself, even if you could do it, which I thought Tony was suggesting maybe you actually couldn't, because, Tony, did I understand correctly, even if you curated the data, the biases are so deeply embedded that even a subset of curated data is still going to be biased, correct? Okay. So that leads me then to the question of the issue of the diffusion of responsibility, because even if you could improve, right, in some way of curating or whatever, but if that problem still persists, then doesn't that still make the diffusion of responsibility issue also really quite intractable? I'm just wondering what you think about that.
Yeah, no, I think that's a really good point. I think what I'm saying is when my idea of curating would be like, rather than taking the whole internet and trying to filter some bad stuff out, you would like very meticulously pick what's in the data set, right? And yes, it would still have biases and stuff like that, but they would be much smaller data sets that we particularly choose to be there, right? So it's not a matter of like, we start with everything and then try to filter through it and curate based on that. It would be like, no, I'm going to choose, these particular books and these particular, conversations that a group of people has decided are going to be much safer to train on. So this type of curation would have to be at a much smaller scale, and I think it would require a network that was actually able to train on smaller data sets. So that's really my answer. We're going to need smaller data sets that we meticulously curate. We can't do the thing where we start with the whole internet and then you're right, it's completely intractable to try to do something like that. So I think that what we need to do is make machines that don't require that scale of data to be able to do the same thing.
Well, I think the fact that the EU is beginning to try to set some controls on things is a good beginning. But maybe I'm having a philosophical dystopian point of view on this. The battle of the AIs, to have AI check out and spot the more difficult or the bad stuff that the criminals will get involved with. Criminals will try to stay one step ahead of what's going on. And I think that's sort of humanistic in nature, isn't it?
Yes, absolutely. I mean, that's a good point, right? So then we have the, then they'll just figure out how to trick the vetting AI that's telling us, what's made, And I think that's always going to be an issue. I'm not sure we're really going to get around that. I don't really know. Like you said, criminals are going to try to stay one step ahead and trick these systems and get past these safe rails and so on and so forth. And that just means that we're going to need to stay on top of it and then update these systems and make sure that we catch these new unique types of cybersecurity attacks and so on and so forth. And I think that, that is a whole, there are a bunch of people worrying about this type of stuff, but yeah, we would definitely need to be active and not just, set off these AIs and be like, oh, well, our job's done. Hey, it's taking care of it. We can go home and we don't have to worry about it. It's like, no, if it's taking care of it, we're going to need to stay on top of it. Yeah, I think that's a really good point.
Hi. I'm just thinking that, is there really any learning that is not biased?
Good question. No.
Yeah. So in this respect, I mean, yes, we can curate and try to do, and there is always, you call it bias, or you go with preference, or you call it cultural difference. Learning is biased.
Yeah.
And I think that what you said about the EU is probably the right way, actually, to have some structure and protection for all of this. And the other thing that came to mind when we were thinking of every difference between AI and anything else there before, I mean, just if you think of the computers as being these universal machines, a car you drive, and basically in a computer you can do anything. So this is where, for me, AI gets so scared. It's not just the scale, but this proliferation into absolutely everything.
Absolutely, yeah. So, I mean, yes, I do think it's going to be biased. I mean, I guess if you think about bias in general, right, there could be good biases and there could be bad biases, right? It could be biased towards treating people equally. It could be biased towards treating people unequally. And in that sense, that there's always going to be some kind of bias there. I think, like Tony mentioned before, majority of these are only trained on English text, right? Especially, there's also like things like translation algorithms that aren't trained on enough like Tagalog or other languages that it's never even seen before, and they're supposed to be translating these texts and they're doing a bad job. Those are the types of biases that I think I was talking about. This sort of enforced inequality in the data set. But I do agree, I don't think we're going to be able to escape the problem of bias by curating these data sets, but we can certainly reduce the amount of inequality in the treatment of people and the way these things behave. So, I mean, I think a lot of these issues, like the question before this and this question, like these are fundamental issues for humanity that go way beyond AI, right? And these are things we should definitely be concerned with. And I do agree that I think EU is definitely making the right move here, trying to get at it pretty early and put some guardrails into place. And then they can continue to iterate and keep updating these rules as we get new technologies. I think that's the only way we're going to be able to deal with this. The whole Wild West approach, free market approach is extremely dangerous at this time. And we need to avoid, just making the, white male English speaking perspective the default general perspective in AI. That also, once again, goes way beyond AI and it goes to government and law enforcement and all these other things fundamentally. So I don't know if we're going to escape it, but we certainly need to make efforts to reduce these types of harmful behaviors.
I think at the end of, I think you kind of just said what I was trying to put out in. I don't know if I'm going to push back in a way. So I don't think we are talking really about AI as much as we are talking about human nature. I mean, AI is just reflecting the kind of stuff we are feeding into it. I mean, we are creating the AI and we are feeding the information to it. So to the extent that we are giving, all that information is bringing, it's almost like a mirror to ourselves, right, as a society. So the idea of curation sounds fantastic, and I agree with you. I mean, you have good ideals. You can narrow the information. but at the very end of the day, somebody has to make this kind of decision, right? So to what extent shouldn't we just let AI kind of like at some point learn to decide on its own? You know, what kind of information should be the one, I mean, let it curate its own sources of information. Because I think it feels to me like the more we are hands-on trying to guide AI, the worse it gets. The more we are influencing, putting our own nature into it. Shouldn't we allow it to be detached from us so it can grow in a better way or worse? I don't know. I don't know where it's going to go, but it seems like we are like an anchor to AI in a way.
I guess the problem is, though, that if you were to do that, it would then just, once again, still be trained on the whole internet and just be that mirror, except now we're not even intervening on when it does bad things. So it's going to need to develop its own sense of morality or something like that, which especially these models certainly don't have. I don't mean they could, I guess, in principle have something like that. I just don't. I certainly wouldn't trust them to regulate themselves, because I guess the problem is that these corporations are the ones training them. So then what that is a free ticket to say, okay, well, I'm a big corporation. I'm training this AI. Oh, don't worry, I'm going to train it to be nice. And it's gonna curate itself, and then no worries, right? And I think that's kind of a dangerous path. That speaks to like Lucy Sussman's point about the thingness, right? We make it a thing in itself, and it's no longer our own responsibility. It has its own responsibility to be moral. But like still, I don't think your idea is like not fundamentally mistaken. I think, like we were saying before, having the AI curate things and be able to tell what's information and misinformation and all those things, it seems like a necessity. Right, but I don't know if it's already trained on all of this human data, it's already going to be the mirror, and if we then intervene to make sure it behaves a little bit better, I don't think that that's a bad thing.
I'm more interested in like the neuroscientist side of this you had. We always hear like AI can help us understand how the brain works and things like that. And then you had good examples of how you're using it. But I was just wondering, in terms of the future of neuroscience and psychology, like what role do you see AI playing?
Yeah, no, I mean, it's definitely, I see it playing a bigger and bigger role. I think that these particular networks that we've been talking about today are very far removed from the way the brain actually works. Although it can predict some brain activity, it really does not work in the same way the brain works. For us to use this to understand the brain, we're going to need to make these artificial units, much more complex. And we're going to need to make them mimic the types of brain cells that we observe, right? And I think that's very possible. So I think that's really the future, is to make more biologically realistic units and then figure out the relationships between those units. It's quite difficult to do that. That's why we're using these simplified models. But I don't think that it's impossible. I certainly think that as we learn the relationships between these simpler models, we can then use that to make them more biologically realistic, and then figure out some more fundamental properties of these types of networks of cells. So I think it's definitely where the field's going. Computational neuroscience is going to be way more part of the neuroscience curriculum in the next 50 years. There's no doubt in my mind. And we're going to see all of these biology majors are going to have to start taking more of these computer science classes in order to understand some of these very large data sets and build models that are much more biologically realistic. So yeah, that's a great question. And yeah, I definitely see it moving in that direction. But I do think the point is that in its current instantiation, they are not human brains. Although people will tell you they are. They'll be like, of course, it's the same, right? It's really not. They are fundamentally different, much more simplified. Human brains have about 80 billion neurons. ChatGPT has, between 175 billion and a trillion. We don't even need that many. Not only that, think about this. This is another point about the brain. Okay, so like ChatGPT, like we said, it uses 1,000 households for 1 year worth of electricity. The human brain does not at all use anything like that, right? We have 80 billion neurons, and we're like, you eat like a Nutri-Grain bar, and it's operating, right? So what's the difference there? If we had more biologically feasible neural networks, then the carbon footprint of these networks would be like a Nutri-Grain bar. So that's why we should definitely be looking to neuroscience for these types of answers, and I think that's why these mechanistic explanations, that's certainly why we're trying to relate those two things in mechanistic explanation. But it's not going to be easy, so it's gonna take a while.
I'm a computer scientist, so I just would like to make the comment that actually what is needed is also for computer scientists to take more neuroscience and psychology and philosophy courses, because these models are being developed by computer scientists. All the metrics, so differences are measured, symmetric differences and stuff like this, that absolutely they're experimental data that this is not how humans and how the brain work. So this idea that we are different silos and everybody works independently, they really have to go down, and we have to be much more integrated and interdisciplinary.
Absolutely, I totally agree. Yeah, my degree was in interdisciplinary work, so we try our best to work with computer scientists and biologists, etc. But in general, yeah, computer scientists, they don't have to take biology classes, nor do they actually even care about the brain question most of the time. Not everyone, of course, but a majority of computer scientists, what they want to do is make the error go down better. They want to train networks to perform a little bit better. And then a lot of times, like a big computer science paper will be like, we have 1% better performance with this special network. And that's what we care about, getting the performance to do better. And it doesn't really matter if it's like the brain. They don't really care, to what degree it's related. But I think that if we want to move in the right direction, just like you said, yeah, computer scientists should be exposed to neuroscience, especially if they're doing deep learning, And in the 80s, with the connectionist movement, the early neural network movement, they were very much like interested in that relationship. As deep learning got more and more popular and the used for a wide variety of things, it just became unnecessary to worry about its relationship to the human brain. Forget about the human brain. We have these networks now, and we can just worry about them. I think that's a recipe for not thinking too critically about these networks. And like we said, the Nutri-Grain bar example, like that seems like a good motivation to figure out how biology works if we can make these things more energy efficient. But most computer scientists would be like, I just want to get the 1% in performance.
We have time for one last question here.
Great.
So I think you mentioned in one of the labs that artificial networks are being used to model some neuropathologies. So along kind of the same lines as the previous question about the neuroscience aspect of what AI could help with in the future, do you see a role for AI to be used in modeling neuropathology or in innovating treatments, or is that what's already being done?
Yeah, no, I think absolutely. Yeah, it can certainly be used for pathological states and things of that nature. It can also, just be used to figure out how the brain works in general. But yeah, I think also in this case, your model would have to be similar enough to the brain where when it fails in similar ways. And in fact, I think that's when you have a good model. If it would have pathologies that are similar to our pathologies, then that your model is actually working in a really clear way. So yeah, we're certainly doing that type of stuff. Not as much as you'd think. I think we're using the networks to model the behavior and then studying the differences in the behavior. But you could certainly look and try to make models of brain diseases. And it's actually, believe it or not, really easy to make a neural network have a seizure. It's actually more easy to make it have a seizure than not have a seizure. So most of the configurations of the artificial neural networks will just generate a gigantic seizure, and then you actually have to have very, very particular structure to make it operate the way we operate. So there's lots of examples like that, and yeah, it's a super interesting area of research.
Eric, thank you so much. That was splendid. That's all the time we have. Thank you so much.
Thanks.